Hello, my name is Sergey Gorodetsky. I'm an associate professor at the Department of Higher Mathematics at Moscow Institute of Physics and Technology. Now we're going to consider the solutions of the contest MIPT-International, that is Moscow Institute of Physics and Technology International, and contest of mathematics. We have a problem set of the 11th grade to consider right now, and you can see the first problem on your screens. Here in the first problem we're facing a trigonometric equation and we just need to solve it, so nothing special in the task. We start with simplifying the left side of this equation. That is, we can use a trigonometric formula for sine of the double angle, and then the left side looks like, not the left side, but the first fraction looks like 2 sine of x minus 2 sine of x cosine of x, and in the denominator we're going to have 2 sine of x plus 2 sine of x cosine of x. As for cotangent squared, we can write it down as cosine squared, keeping the same argument, divided by sine squared. And we have 14 on the right. What are we going to do next? The first fraction can be reduced by 2 sines of x, and this way we have 1 minus cosine of x divided by 1 plus cosine of x. As for the second fraction, its numerator is equal to 1 plus cosine of x divided by 2, and its denominator is equal to 1 minus cosine of x divided by 2. And we still have 14 on the right. These ones are reduced, and after that we can bring the fractions on the left to the common denominator. And so we have 1 minus cosine of x squared plus 1 plus cosine of x squared, and in the denominator we have difference of squares, that is 1 minus cosine squared of x, and we have 14 on the right. Expanding and combining like terms in the numerator yields 2 plus 2 cosine squared of x. The denominator remains unchanged, and we have 14 on the right. Now we can multiply both sides by the denominator, and I guess we'll simultaneously reduce the equation by 2. So we'll have 1 plus cosine squared of x is equal to 7 minus 7 cosine squared of x. Expressing cosine squared of x out of here, we'll have that cosine squared of x is equal to 3 over 4. Now either we can find the values of cosine of x, or we can use a trigonometric formula to transform the left side and get 1 plus cosine of 2x divided by 2 out of it. So it is still 3 over 4 on the right. And then we'll get only one elementary trigonometric equation instead of 2. So we have cosine of 2x is equal to 1/2. Therefore, 2x is equal to plus or minus pi over 3 plus 2 pi k, where k is an integer. And dividing everything by 2, we get x is plus or minus pi over 6 plus pi k, where k is an integer. And that's the answer to our problem, but we still need to do one more action. we do not have to forget about the domain of the initial inequality. And in the initial inequality, we can see we had a denominator here, but we also had a denominator in the cotangent. So this was one of the denominators, and this is the second one. The first denominator is factorized and can be written as 2 sines of x multiplied by 1 plus cosine of x, and it has to be different from 0. As for the second denominator, it has been converted into 1 minus cosine of x divided by 2, and therefore 1 minus cosine of x has to be different from 0 as well. But we can see that 1 plus cosine of x, 1 minus cosine of x, and sine of x are not zeros for the values of x we have found. And therefore, this is the answer to our problem. And now we can move on to the next problem. So we have two arithmetic progressions or arithmetic sequences, and we have to find the sum of the first 80 common terms of these sequences. So the first sequence has a common difference of 11, whereas the second one has a common difference of 5. These common differences are co-prime numbers, so that are numbers that do not have any common divisors besides 1. And it's not that difficult to prove that a sequence that consists of common terms is going to be an arithmetic sequence with a common difference of 55. So 55 is 5 multiplied by 11. But as for now, we need to determine the first common term of this arithmetic progression. In order to do it, I guess the easiest way is just to write down several terms of the first progression and of the second progression, and this way we'll notice which is the first term that coincides. So maybe we start with this one: 4, 9, 14, 19, 24, 29, 34, 39, 44, 49, 54, 59, and so on. As for the second one, these terms, they increase faster. And I can see that 49 is the first common term in these two progressions. So that's it. If we call our progression for AK, then A1 is 49, and if D is a common difference, D is 55. Therefore, our progression looks like AK is A1 plus 55 times D minus 1. And now we need to find the sum of A1 plus A2 plus and so on plus A80. This sum is given by, it is standard formula for sum of consequent terms of an arithmetic sequence. So this sum is equal to half of the sum of the first and the last terms, that is A1 plus A80 over 2, and multiply by the quantity of the terms, by 80, that is. So we have 40 times A1 plus A80, but A sub 80 is equal to A1 plus 79D. And at the same time, I reduced 80 by 2 and got 40. Now everything has to be substituted into this formula, and we'll get the answer. So that is 40 times 98. 98, it was a1 plus a1, and plus 79d plus 79 times 55. And it can be calculated up to the end, but I guess you'll be able to perform this section by yourselves. In our next problem, we're facing an equation with a logarithm. So we have the equality of two logarithms. The bases are different, but they resemble each other quite a lot, yet they're different. And the expressions under logarithms are also different. So the question arises, how can we deal with it? What can be done? And first of all, we can notice that the expressions under the logarithms are similar to each other. That is, here we have this quadratic polynomial. And if we remove 6 from here, we'll have the same quadratic polynomial here, but multiplied by -1. So without this 6, it is just the same as here, but multiplied by -1. Consequently, it seems to be reasonable to introduce a new variable, for our equation looks more compact. And let it be x squared plus 2x plus 2 roots of 2. And it has to be equal to something. Let's call it for t. And now we have logarithm with a base root of 26 plus 5 of t, and on the right we still have a different base, and we have 6 minus t under the logarithm. Now let us look more closely at the bases of these logarithms. The base of the first is root of 26 plus 5, and the base of the second is a conjugate number. So we have root of 26 minus 5. But if we multiply two conjugate numbers by each other, we can use the difference of squares, and guess it is not a mere coincidence that we have a result of 1. Having this 1 as a result, it allows us to write down that root of 26 plus 5 is just 1 divided over root of 26 minus 5. Alternatively, it can be rewritten as root of 26 minus 5 to the power of -1. And therefore, the left side of our equation can be written as logarithm with base of root of 26 minus 5 to -1 t, and that is minus logarithm of t with base of root of 26 minus 5. And after having transformed the left side this way, we have that both logarithms have the same base. Perfect. Then we can move them to one side, and our equation becomes logarithm of 6 minus t plus logarithm of t equals 0, or having the same basis, we can rewrite it as a logarithm of a product. And it yields that 6t minus t squared is equal to 1. Now that's a quadratic equation. There is nothing difficult in solving it. So t is 3 plus or minus 2 roots of 2. And these are the roots. We do not have to forget about the domain of our equation, and So let's look at the equation we obtained directly after having made our substitution. From the first logarithm we can see that t has to be positive, and from the second we conclude that t is less than 6. Therefore, the interval for t is from 0 to 6. And we can easily check that both these values of t, they belong to this interval. Hence, they both satisfy the equation. It could have happened this way, that one of these values, or both of them, do not belong to the domain of our equation. In fact, it would have been easier, so in that case, we could have written that the equation had no solutions, and that would be it with the problem. But now we have to proceed. We have to go back to x and to express it right from here by substituting t for the values we have found. And let's see where we're going to get. So x squared plus 2x plus 2 roots of 2 is equal to 3 plus 2 roots of 2. And x squared plus 2x plus 2 roots of 2 can be equal to 3 minus 2 roots of 2. In the first equation we can cross out 2 roots of 2, and we'll get x squared plus 2x minus 3 is 0. And in the second one we get x squared plus 2x plus 4 roots of 2 minus 3 is 0. Then the first equation yields that either x is minus 3 or x is 1. What can we tell about the second? We can find the discriminant of this equation, and in fact it's easier to get 1/4 of the discriminant because this coefficient is even. And 1/4 of the discriminant is 1 minus 4 roots of 2 minus 3. That is 4 minus 4 roots of 2. And we can see that it is negative, and so the second equation yields no solutions. Hence, the answer to our problem is minus 3 and 1. So there are 2 roots of the equation. Okay, the next problem is a geometrical one. Okay, so we can see that angle ACB is equal to 90 degrees, and it means that we have a right triangle. Then we have 2 angle bisectors. One of them goes from the right angle, and some other bisector. I don't know which one to choose yet, so let it be this one. So 2 angle bisectors. Okay, and so this one is called CF. They intersect at point O, and another bisector is called BE. That's A. All right. And we know the values of BO and OE. We start our solution with applying the angle bisector theorem, that is the property of a bisector that is used in quite a lot of problems where we have a bisector of a triangle. And so it says that bisector divides the opposite side in the same ratio as the ratio of two other sides. So the ratio of BO to OE is equal to that of BC to CE. But from the task we can see that BO and OE are in the ratio of 3 roots of 29 divided by 6 roots of 29 over 5. Root of 29 is reduced here, and we'll get 5 over 2. As we have formulated, the angle bisector theorem implies that BC and CE are in the same ratio. So if we introduce the notation that BC is 5x, it immediately means that CE is equal to 2x. In the same way, we can apply the angle bisector theorem to triangle BCA and its bisector BE. We also understand that AE and CE are in the same ratio as BC and BA. And so if we denote AE as 2y, then we conclude that AB is equal to 5y. So these segments have to be in the same ratio as these ones. As the ratio here is equal to y divided by x, this ratio also has to be equal to y divided by x, and that's why the length of AB is equal to 5y. And now we only need to use Pythagorean theorem twice. First we do it for triangle BCA. Oh no, not BCA, but BCE. There is only one variable here, it is x. So the legs of this triangle are expressed through x. And as for BE, it is known, and we get 4x squared plus 25x squared is equal to, let's calculate the value of BE. Let it be somewhere here. So it is 3 plus 6 over 5 root of 29. That is 21 over 5 root of 29. So it is 21 over 5 root of 29 squared. And now we can notice that the coefficient of x squared on the left is 29, and so we can reduce both sides of this equality by 29, and we have x squared is equal to 21 over 5 squared, and x is equal to 21 over 5. Obviously, the negative value of the negative solution of this equation being unacceptable. So we only have 21 over 5. And after that, we use Pythagorean theorem for triangle ABC, and we have 2x plus 2y squared plus 5x squared is equal to 5y squared. Now we expand everything and combine like terms, and let's see what we have. For example, we move all the terms to the right. So we'll get 21y squared. After that, how many xy are there? We have 8xy on the left, and we move them to the right. So we'll get minus 8xy. And finally, 4x squared plus 25x squared. It sums up to 29x squared, and moved to the right, it becomes minus 29x squared. This can be considered as a quadratic equation with respect to y, and we can find its roots in a usual way. And so either y is minus x or y is 29 over 21x. The first root is not appropriate here, for y and x are positive values, and so we only have the second one. But from the second one we get that y is equal to 29 over 21, and if we substitute x for what it is, we'll get that y is 29 over 5. And now, knowing the values of the legs of the triangle, so knowing BC and AC, we can easily find the area of our triangle. That is, AC is 2x plus y, and as far as I understand it is 20. BC is 5x, it is 21, and consequently the area of triangle ABC is 1/2 times 20 and times 21, and it is 210. And our problem is solved, and we can proceed with the next one. Okay, so here maybe you need a little time to read through that task. It contains quite a lot of text. In fact, it is not that difficult to solve, but one has to be careful in order not to get confused. So, two types of monkeys, marmosets and chimpanzee, and they have found some dried fruit. Okay, dates and bananas. Let's introduce some variables. Maybe it's better to make some table. Let's say these are marmosets, these are chimpanzees, these are dates, and these are bananas. And let's call the amounts found by marmosets by x and y. So x and y are just the values to be determined. We're asked to find them. And near these values, let me note that during the first day, marmosets have eaten 1/11 of dates. So I'll write down the part of dates they have eaten, and 1/4 of bananas. Then, how much fruit have the chimpanzees discovered at their supply? They have discovered 22 kilograms more of dates, that is x plus 22, and 66 kilograms less of bananas, that is y minus 66. And as for the chimpanzees, they have eaten 1/4 of dates and 1/9 of bananas. Now let's look at the, let's continue reading the task, and let's look at the conditions we have here. It is known that chimpanzees have eaten 4 kilograms of dates more. Okay, if they have eaten 4 kilograms of dates more, it implies that x plus 22 over k minus 4 is equal to the amount of dates eaten by marmosets. So x divided by 11. and they have eaten 6 kilograms of bananas less. So y minus 66 divided by 9 is by 6 less than the amount of bananas eaten by marmosets. So if we add 6 to this amount, we get a greater amount, the amount eaten by marmosets. All right. As for now, and furthermore, we know that k is an integer. Of course, without this condition, we couldn't have solved this system of equations, so we would have been able to express x and y through k. That would be it. As for here, the system can be solved in slightly different ways, but I suggest that we express k from each of the equations. To do it, we move this term to the right in the first one and bring the terms on the right to the common denominator. So we'll get x plus 22 over k is equal to x plus 44 over 11. And from here we can express that k is equal to 11x plus 22 divided by x plus 44. And in the second equation we do not need to move anything to another side. We just bring the terms on the left to a common denominator, and it yields y minus 12 divided by 9 is equal to y over k. Hence k is equal to 9y divided by y minus 12. And now let's look at the equations more intently. From the first equation I can see that its right side cannot exceed 11. Why is it so? X is a positive variable, and therefore x plus 22 is smaller than x plus 44, both of them being positive. And x plus 22 divided by x plus 44 has to be less than 1. But if I multiply some number that is less than 1 by 11, I'll get a result that is less than 11. So from here it follows that k is less than 11. But now let's look at the second one. The reasoning is quite similar, but first of all let us notice that y has to be greater than 12 for y is positive. Otherwise, it would happen that a fraction is going to be negative, but it is not possible for k is obviously a positive number. It follows from the task. One cannot eat, for example, minus 1/5 of the supply of bananas. It doesn't make any sense. And so this fraction has to be positive, and therefore y is greater than 12. But if y is greater than 12, we have that the numerator and denominator of this fraction are positive, and if we don't take this 9 into account, without it, this fraction is greater than 1, for its numerator is greater than its denominator. But if multiplied by 9, it becomes greater than 9. Let me better write it as k is greater than 9. And so we deduce that k is equal to 10, the only possibility because k is an integer. And knowing the value of k, we can substitute it here and express the corresponding values of x and y, so there is some technical part of the job left for us to do. So if k is 10 and I multiply both sides of this one by the denominator, I'll get 10x plus 440 is equal to 11x plus 242, and so x is equal to 198. As for the second one, we'll get that 10y minus 120 equals 9y, and it is even simpler than the previous one, so y is equal to 120. And in fact, that is the answer to our problem, so we can state that marmosets have found 198 kilograms of dates and 120 kilograms of bananas. And by the way, they have eaten quite a lot, so they must have been hungry at the start of our problem. Okay, now having dealt with the marmosets and chimpanzees and dried fruits, we can go to the problem with the parameter. So we have two equations. Only one of them has a parameter in them, so the second one and we need that only one value of y satisfies both equations. The problem could have been formulated in a different way, so we could have said that we have a system of two equations and the system has to have exactly one solution. That is an alternative formulation, but never mind. I guess that we can start with the first equation, as it doesn't contain a parameter at all, so there is no p in here. And I guess it's reasonable to solve it. In order to get rid of the absolute values, we'll have to consider several possibilities. And we start with factorizing the expression under the absolute value. So it yields y minus 1 minus 6 multiplied by y minus 3. And there is a second absolute value here. It is y minus 2 under the absolute value. And it's, in order not to get confused, it's better to draw a line, real line, and so we have points 2, 3, and 6, where the expressions under the absolute values turn to 0. And these 3 points, they divide our real line into 4 intervals, and basically we can consider these intervals. Let us start with the first one. So the first one is when y is less than 2. It can be easily checked that the expression under the first absolute value is positive here, whereas the second one is not positive, so it is either 0 or negative. Therefore, the first absolute value is just omitted, whereas when omitting the second absolute value, we'll have to put an extra minus here. It will yield, so the first interval, y squared minus 9y plus 18 minus 9y squared plus 31y minus 22, and an extra minus here, 10 times y minus 2 squared. And it is equal to 0. In fact, here we have just to simplify this equation, so we need to expand the parentheses, we need to combine like terms, maybe reduce the resulting equation by something. And all in all, we'll get y squared, 9y squared minus 31y and plus 22 equals 0. As the sum of the coefficients is 0, we can find that either y is 1 or Another root can be found from Vieta's formula. That is, we get that product of the roots is 22 divided by 9, and so the second root is 22 over 9. As right now we're considering this interval from minus infinity to 2, we can see that only this root belongs to this interval, so the second one doesn't suit the equation. So it is. This one is okay, and this is the one we do not need. Now let us move on and take the second interval into consideration, from 2 to 3. From 2 to 3, we'll get that the expression under the first absolute value is non-negative, but the same is true for the expression under the second absolute value. Hence, we'll get y squared minus 9y plus 18, then the part that didn't have any absolute values at all. And the difference is that we're going to have a plus here instead of a minus we had before. Combining the like terms and simplifying everything, we'll get y squared minus 9y plus 18 equals 0. And that means that either y is 3 or y is 6. In fact, when we consider this interval, we can include 3 into it, and so 3 is the root of our equation. As for 6, it doesn't belong to this interval, so we'll put a minus here. Now we go on, and interval number 3. What has become different compared to the previous interval? If we have moved through this point, it means that the expression under this absolute value has changed its sign. So it was positive on the previous interval, and it's going to become negative here. Thus we have minus y squared minus 9y plus 18 minus 9y squared plus 31y minus 22 and plus 10y minus 2 squared. And it has to be 0. Expanding and combining like terms in this equation, we'll see that it yields 0 equals 0, and it means that all values of y on this interval are roots of our equation. So we have that y belongs from 3. 3 is excluded right now, for we have considered it in the previous interval. So from 3 to 6, and nobody prevents us from including 6 into it. In fact, as for interval number 4, if we're attentive enough, we can see that interval number 4 represents the same situation as interval number 2. That is, both expressions under the absolute values are non-negative. And so we do not need writing it twice. In fact, instead of interval number 4 here, I can write that it is like second case as well. So then it is not an interval number 2, but there are several cases. First case, the second, that corresponds to 2 intervals, and the third case. All right, and now, after all the intervals have been considered, we need only sum it all up and write down all the solutions we obtained. So all in all, we can see that y belongs to 1 and an interval from 3 to 6. And let's solve it with the first equation. Unfortunately, it has infinitely many solutions. So if it happened that this equation had, for example, two solutions or three solutions or something, we could have solved this problem in the following way. We could have substituted the solutions of the first equation into the second and find such values of parameter that they satisfy this equation. But we cannot substitute an infinite number of solutions as we have it here, and so we have to deal with the second equation somehow. But the second equation is quadratic with respect to y. It can be used by applying the standard formula for solving quadratic equations, but I guess here it's better to use Vieta's formula. And let's see. The constant term, that is the one that doesn't contain variable y, can be factorized, and this equation becomes the following. But now we can see that the product of roots of this equation is equal to p plus 4 times p plus 6, and the sum of the roots is 2p plus 10. I think now it's become quite obvious that the roots of this equation, let us call them y1 and y2, they're equal to p plus 4 and p plus 6. By the way, it's also interesting to notice that these two roots are different for all values of p. So it happens that this root is exactly by 2 greater than the first one. Sometimes when we have roots given by a formula with parameter, formula can be different, but it doesn't prevent them from coinciding for some values of parameter. And here the formula have this specific, we have this specific situation that y2 is for all values of p by 2 greater than y1. And so two different roots here. And now I guess it's become clear how we can find the values of p we need. In fact, we need that exactly one of these roots belongs to the set of the solutions of the first equation. So either p plus 4 belongs to this set and p plus 6 does not, or vice versa. Let's see when does p plus 4 belong to this set? I guess we can make it this way. So p plus 4 belongs to the set of either 1 or interval from 3 to 6. It is equivalent to the fact that p belongs, we just need to subtract 4 from all the numbers we have here. So minus 3 and minus 1 to 2. And in just the same way we determine such values of p, that p plus 6 belongs to this set. It means that p belongs to minus 5 and an interval from minus 3 to 0. Okay. And we need such values of p that they belong to exactly one of these two sets. It is so-called disjoint union of these two sets. So usual union consists of such values of p that belong to at least one of the sets, so it doesn't prevent p from belonging to both sets. But disjoint union consists of such values of p that belong to exactly one of the sets. So we have that p belongs to minus 5, and then minus 3 is not suitable, So from -3 not included to -1 also not included. Then the whole interval from -1 to 0 is unacceptable, and therefore we'll have from 0 to 2. And that's the answer to our problem. And we're facing the last problem, one more geometrical problem. We have a trapezoid that is inscribed into a circle. So we remember that any trapezoid inscribed into a circle has to be isosceles. And I guess that it's better to start the solution with making a sketch. So let's draw a circle first. We have its center somewhere. We have the basis of our trapezoid. CD is the smallest base and AD is the largest. We have a center of our circle somewhere. And let us start our solution this way. So I draw a diameter that goes through the center of the circle, and such diameter that is perpendicular to the basis of our trapezoid. After that, I'd prefer to connect point O, so let the center of the circle be O, with vertices A and D of the trapezoid, and we know that arc AD is equal to 120 degrees. Means that the corresponding central angle is also 120 degrees. Now, if we denote this angle as alpha, we can calculate that this one is 60 degrees minus alpha, as all these three angles, they sum up to 180 degrees. So here we have 60 degrees minus alpha. And let me also call the radius of a circle as r. Now let us consider this right triangle. By the way, the points of intersection here, they divide the basis of our trapezoid into two. It is a known fact that diameter to perpendicular to any chord bisects this chord, so it divides it into two equal segments. And so we know that, let it be AH, for example, and DP. So we know that AH is 11 divided by 2, and DP is just 2 divided by 2, that is 1. And now we can make two equations from triangles AOH and OPD. So if I multiply r by sine of alpha, I'll get dp, and that is 1. That is my first equation, that r sine of alpha is equal to 1. I get the second equation just in the same way from triangle AOH. That is r times sine of 60 degrees minus alpha is equal to AH. And AH is 11 divided by 2. Now, in order to get the radius, we just need to solve this system of equations. Not a very difficult one, although it requires some knowledge of trigonometric formula as well. So would be complicated to solve this problem without using any trigonometry. It's possible, but more complicated. All right. So what am I going to do with the second equation? I'm going to expand sine of 60 degrees minus alpha and multiply both sides of this equation by 2. So I'll get 2r sine of 60 degrees cosine of alpha minus sine of alpha cosine of 60 degrees is equal to 11. Now remember the values of sine of 60 degrees and cosine of 60 degrees. So I expand the left side and substitute these values instead of sines and instead of a sine and a cosine. I'll get r root of 3 cosine of alpha minus just r sine of alpha is equal to 11. But knowing that r sine of alpha is 1, we can conclude that r root of 3 cosine of alpha is 12. So r cosine of alpha is 4 roots of 3. And now having these two equations, we can divide one of them by another one. It doesn't matter how we do it. For example, I can divide the second by the first. Doing this, I'll get that cotangent of alpha is equal to 4 roots of 3. But I know that cotangent squared of alpha plus 1 is equal to 1 divided by sine squared of alpha. This formula can be obtained by dividing both sides of trigonometric identity, that cosine squared plus sine squared sum up to 1, by sine squared of alpha. And knowing cotangent of alpha and substituting it into the formula, we get that sine of alpha is equal to 1/7. Obviously, the negative value of sine is unacceptable here for alpha, cannot exceed 180 degrees, and so sine of alpha is positive. Just wonder if we need cosine of alpha at all. It can be found, of course, but I doubt if we need it. Well, if we need it further on, there is no problem to multiply cotangent by sine and get a cosine this way. But I can see that a radius can be expressed without knowing the value of cosine. So radius is 1 over sine of alpha, and that is 7. And in fact, we have solved the first item from this task. Now to the second item. We're given some extra information. We have an extra point F that belongs to base AB of our trapezoid, and such as that AF is equal to 2. Then we draw a line CF, and it intersects the circle at point T. And we need to find the area of triangle COT. In fact, to determine the area of a triangle, knowing that one of the vertices of this triangle being its center, we only need to know the distance from point O to this chord, to CT. Indeed, if we have a circle we know the radius of the circle. We have determined, and it happened to be equal to 7. And so if we know the distance from the center of the circle to this chord, it would be easy to find the chord itself by using Pythagorean theorem for this triangle, for example. So it has a midpoint of the chord. We use Pythagorean theorem for this triangle, and knowing a radius and a distance, we'll be able to find 1/2 of the chord, and so the chord itself, and after it, the area of a triangle. So we understand that our goal is to find the distance from O to chord CT. Okay, in order to do it, let us drop a perpendicular from O on CT. But first, let us notice that, in fact, a quadrilateral CFAD is a parallelogram. Why does it happen this way? We know that CD and AF are parallel to each other as their bases of the trapezoid, but it is also given in the task that AF is 2 and CD is also 2. And therefore, the opposite sides, AF and CD, of our quadrilateral are parallel and equal to each other. And it implies that AFCD is a parallelogram. Thus, if I drop a perpendicular to AD from point O, it is going to be perpendicular to CT as well. Fortunately, this point is it happened to be quite close on my picture to the center of the circle itself, but the center and this intersection point of a perpendicular with CT, they're two different points. And let me call this point, for example, as F. Oh no, I already have F. Let it be E then. And this point, it is midpoint of CT. Let me call it N. All right. As for OE, I can find it from triangle OAD. This is a triangle that this is an isosceles triangle, as its sides OA and OD are equal to the radius of our circle, and the angle between equal sides is equal to 120 degrees. Okay, then we can find AD and OE in different ways. For example, I can write down that OE is equal to OA times cosine of 60 degrees, and I'll get 7 divided by 2. All right. As for EN is in fact the altitude of this parallelogram. But to get the altitude of a parallelogram, knowing its sides, we only need to get the angle of this parallelogram. So now we're looking for this angle, or this would be just more convenient to draw it here. The trapezoid is isosceles, and therefore the angles adjacent to one of its bases are equal to each other. And to get this angle, I drop the altitude of my trapezoid from point C. So let it be C. I'm in need of some letter, M. Okay. As my trapezoid is isosceles, I can calculate that BM is equal to 1/2 of difference of AB minus CD. And that is 1/2 multiplied by 11 minus 2, so 9/2. So if I call this angle for gamma, then I have that cosine of gamma is Bm over BC. And I've forgotten to get BC. BC is the same as AD, and it can be obtained from just the same triangle. But what is the value of BC or AD? It can be calculated, and it is equal to r multiplied by root of 3. And so it is 7 roots of 3. So Bm is 9 over 2, and divided by BC, 7 roots of 3. 3 roots of 3. I reduce my fraction by root of 3, and divided by 14. But then we can express that sine of gamma is equal to square root of 1 minus 27 over 196. So root of 169 over 196, so 13 over 14. And therefore, En is equal to AF times sine of gamma. How do I get it? I can drop an altitude from here, from point F, on base AD of the parallelogram, and as it is a parallelogram, this altitude is equal to the one we need. But this one, drawn with red dashed line, can be determined from this triangle, and so yes, I need to multiply AF by just sine of gamma. Since AF is equal to 2, it yields 13 over 7. And now, knowing both En, so the altitude of the parallelogram, and OE, I can find On by subtracting one of these values from another one. So On is 7 over 2 minus 13 over 7, and it is going to be 49 minus 26. It is 23 divided by 14. So that is On. And now it's better to make a look at this picture. So we know that the distance from point O to the chord is equal to 23 over 14, whereas the radius of the circle is 7. 7 and 23 over 14. Now some technical moments left. We find that CT is 2 square roots of 7 squared minus 23 over 14 squared. And therefore, the area of triangle COT is just 1/2 times CT and times ON, where ON is the altitude of this triangle. And so it is going to be, let me write ON first, it is 23 over 14. And then 1/2 of CT is just a square root of 7 squared minus 23 over 14 squared. Of course, this expression can be simplified. Some factor can be extracted from under the square root, and the final result it doesn't look that nice, but it is as it is. So it is 1265 roots of 3 divided by 196. And that's the area of the triangle we need. So, and the second point of this problem has been also solved. And now I've finished solving the problem set we were going to solve, and I'd like to thank you for your attention and wish you good luck.